Greetings everyone. Today, my group will present to you our Costa Rica household poverty level machine learning project. I'm Marcus, and allow me to run you through the contents. Shiny will introduce the problem statement followed by the data pre-processing and challenges. Lin Yue will take you through our methods, and Randy will cover the results and our best solution. Last, I will close out with some limitations and insightful lessons we learned.
Poverty still remains as one of the biggest global issues today. More than 700 million people, which is 10% of the world's population, still live in extreme poverty. Lack of income and access to resources are the main result to poverty. However, poor people also suffer from malnutrition and related health risks and face social discrimination and exclusion in their daily lives. Worst of all, many a times they are unable to prove that they are indeed poor in order to get the help they need, as necessary details of their income, asset, and expense records are hard to collect and quantify. Through these factors, we are able to understand the immense significance of poverty. Hence, our problem statement is to determine a method to effectively gauge the right amount of aid to be given to each household. This is to ensure misallocation of resources and help those who actually need the aid. To tackle our problem statement, we have decided to work with the Costa Rican household poverty level prediction dataset, which consists of a multitude of attributes describing households in Costa Rica. With the data, we aim to find out the respective target scores of these households, which represent their income level and subsequently corresponds to their poverty level. To help us with the classification problem, we explored a variety of supervised learning algorithms. We took into consideration both mathematical models such as naive-Bayes and k-nearest neighbors, and deep learning models such as multi-layer perceptron and stochastic gradient descent. We also ventured into the idea of incorporating ensemble learning into our project as well, with the usage of multiple gradient boosting frameworks such as CatBoost, LGBM, and XGBoost. Our decision making for selecting which models to experiment with included brainstorming different criteria to place importance on. The criteria we examined were speed, accuracy, being able to handle large data, and how many parameters we are able to manipulate. Usually, the case for this was that if we place more emphasis on one particular criterion, some other criterion would be traded off. Hence, it was vital to find a balance between all of them. The next step was to pre-process the dataset, in which there are 5 crucial steps: dataset acquisition, importing of libraries, data visualization, data cleaning, and finally, dataset formation. Since real-world data is usually incomplete, inconsistent, and inaccurate, and often lacks specific attribute trends, these steps are important to ensure that the data is most useful to us. One of the challenges we faced were inconsistencies in terms of the data format within certain variables. For example, as you can see here, these variables have both string and numerical values. Hence, to make the columns numeric, we mapped all strings to ones and zeros. We also discovered missing values that were marked as NaN. We explored various approaches of replacing the NaN values, such as finding the mean or median value of the target variable, omitting variables containing missing values, padding with zeros, and finding appropriate values based on other variables that might have an impact on the target variable. We also realized that there were certain variables that had partial meaning of a particular household attribute and needed to be considered together with other related variables, or else their actual representation might be misunderstood. Another challenge was the presence of variables that did not contribute any significant meaning, for example, squared variables as seen here. As a result, we decided not to take into account these variables and drop them. Last but not least, we had to deal with variables that had two similar or exact representations but had only different variable naming.
The first model we use is the multi-layer perceptron model. It's a popular feed-forward neural network model that contains 3 main components: input layer, hidden layer, and output layer. The input values will be forward propagated to the output layer, then the loss will be calculated using the loss function. The network will then update the weights and bias using backward propagation. After a certain number of reports, the loss and accuracy will converge at a particular value. We also explored tree ensemble methods based on decision tree, namely XGBoost, LGBM, and random forest. One advantage of using XGBoost is that the trees can learn from the mistakes of the previous model and improve their performance. As decision trees are prone to overfitting, it also uses regularization methods such as shrinkage and subsampling to reduce the effect of overfitting. This model is very commonly used in classification problems as it usually gives high accuracy and has high processing speed. The second one we explored was the LGBM model. As the name suggests, this model is very light as it splits the tree level-wise instead of leaf-wise. Thus, it consumes less memory and has a much faster computational speed. The last ensemble method we explored was the classic random forest model. Each of the trees is generated with a subset of features. The model takes the results from n number of decision trees and obtains a final output using voting. Another model that we have worked on was the KNN model. The KNN model classifies points based on proximity. It's assumed that similar data points will be close to each other. For example, we let k equal to 7, and from the diagram, P has 2 neighbors from class A, 2 neighbors from class C, and 3 neighbors from class B. So in this case, we will classify point P as class B. However, this model can be very prone to error when one of the classes dominates the training data. The last method we explored was the support vector machine, or SVM. This method will draw a boundary between two classes, where the boundary has equal distance from the nearest points of both classes. In the example shown above, the boundary drawn has equal distance from the two blue points and the green point. However, in practice, the separation of different classes is not so simple as the one shown in the example. Thus, we use the radial kernel in this problem, where we find the separation in a higher dimension.
Next, I will be going through the experiments and results. To tune the hyperparameters of our models, we will be using 5-fold cross-validation. We use cross-validation here as the dataset has limited trained data ratio to the number of test data, so we want to use as many points of data to train the models as we can. And cross-validation is suitable here since it allows all data points to both be used to train and to validate the models. For the validation metric, we'll be measuring the macro F1 scores of the models on the validation data. The F1 score is the harmonic mean of precision and recall, and it gives a better measure of incorrectly classified cases as compared to accuracy. The F1 score is also more suitable for imbalanced datasets such as this Costa Rican one, with most classes having a target of 4. And there is a high cost of false positives and false negatives here, as incorrectly classified households may not be able to get the aid they need or get more aid than they deserve. Now, we will be going through the various parameters tuned for the different models. For the multi-layer perceptron, we tune the size of hidden neuron layers and number of hidden layers, both of which affect the complexity of the deep learning model. We also tune the learning rate and the alpha, which is a regularization weight penalty to prevent overfitting on the training data. For the XGBoost model, we tune the max depth, which is the maximum number of nodes allowed from the root to the farthest leaf in the tree, the mean child weight, which is the minimum weight of each node required before a new node can be created, and subsample, which is the ratio of training instances sampled per tree. For the LGBM model, we tune the number of leaves, which controls the complexity of the tree model, the number of tree estimators, and the learning rate. For the random forest model, we also tune the number of estimators or trees created to fit the training data. For the k nearest neighbors model, we tune the number of neighbors parameter, which is the number of closest data points to the current instance to be assessed. For the support vector machine model, we train an SVM with the radial basis function kernel and tune the parameter C, which is a regularization penalty parameter of the error term that lowers misclassification rates. Next, after tuning the hyperparameters of each individual model, We look at their performance on the test data. Here we can see that the LGBM model performs a fair bit better than the others, and the SVM performs much worse. We then implement an ensemble-weighted voting classifier by first wrapping each model inside a bagging classifier and assigning them weights according to their validation F1 scores. Due to the poor performance of the SVM model, it is not added into the voting classifier. We then test the combined model's voting classifier on the test data. Here we see that the test results are 0.397, which means that the voting classifier actually still performs worse than the individual LGBM model. This is possibly because of the disparity in performance between the different models, and perhaps because this multi-class classification scenario introduces more variance and more noise from the poorer performing models. We then try to improve the ensemble classifier by only using the best performing LGBM model. Since the bagging classifier takes in one type of model, we can specify the number of LGBM estimators, and the voting classifier wrapper is no longer needed. There is a large improvement in performance of the LGBM ensemble classifier, and it performs even better than an individual LGBM model. This is attributed to the greater number of models in the pooled vote, and because each model in the ensemble has comparable performance and were independently trained.
Some of the limitations are: 1. The size disparity between the test set and the training set, which tends to overfit easily and generalize worse to unknown data. Our project also has time limitations for model tuning due to the schedule, of course. And then the dataset may be limited in itself to make any conclusive judgment of any poverty levels of a person. I would like to close out with some meaningful lessons. Many engineers try to build wild new solutions for every new problem, but majority of the time, iteration is how this industry moves forward. If the instrument exists, don't reinvent the wheel. We need a sense of direction and project objectives or goals before we dive into any problem, and not the other way around. Always begin with the end in mind. For machine learning projects with multiple people, some form of version control is essential for an efficient working environment, even if we are talking about static serial notebooks rather than normal software scripts here. When we tune models, always work towards the best models parameters available by trial and error, grid search, or any other means. No improvement, however small, should be wasted. And lastly, there are a ton of other metrics that are critical to the problem you're trying to solve, like classification reports, ROC curves, and more. As they always say, accuracy is not everything. And with that, thank you.